Hello. Is my screen visible? Can you confirm it?
Yes.
No one else is joining, so I think we should start. Okay, so um, sir has given you some homework last week, right? Like deriving things. Like you are familiar with saddle point method. We started with some general function e to power entropy. Then we took general form of that. Then we define it through variables theta and phi. Then we took a variable q. If it is q is plus 1, then it's fermion, and if it is minus 1, then it's boson. So let me write it down. So, okay. Okay, so in last week class you got entropy formula, some general formula. is e to the power entropy as a function of u and n, and we got some general form of this as 0 to 2 pi, and with some arbitrary value we didn't define, d theta over 2 pi e to the power I theta u, then integration of 0 to 2 pi d phi over 2 pi e to the power I phi n, and some function of these variables theta and phi. Right. So we took some general form for this entropy for bosons and fermions, and we took this fq theta phi as multiplication of 1 to infinity 1 plus q e to the power minus I theta, this small u, or it's not small u, it's total energy u, and this is total number of particles, is total internal energy. So we have written fq as minus I theta epsilon j e to the power minus I phi to the power q. See here epsilon j, this is the energy of the jth state. If you consider a staircase, then we can generally take their equidistant, means their energy level, for each energy level energy is same something, or we can take that each energy step has different energy, epsilon 1, epsilon 2, epsilon 3, something like that. So any particle staying, any particle or marble, if you consider if it is staying in epsilon 3, its energy will be epsilon 3. If two particles are staying at this energy this level, then this total energy will be 2 epsilon 3, something like that. So this j runs from 1 to infinity. So this j represents the stairs number, which the particle is which stair, like if it is 3, then the particle is in stair 3 and with energy E3, something like that. So sir has defined these variables theta and phi, and we do not know how they are how to measure them, so we need to convert them to our known variables in terms of u and n. These variables we have to convert them, then we can make sense of them. Like, this formula, we don't know theta and phi, how do we calculate entropy of the system? So we need to find this form in terms of our known measured variables E and T, these things. So here we have taken the general form of this entropy, and this Q If it is 1, then it's fermion, and if it is -1, then these are bosons. Fermion means only one particle can stay in one energy level. For bosons, any number of particles can stay in same energy level. So we have defined a general formula for bosons and fermions both. So we will see how to make sense of these theta and phi. Okay. Okay. So the total energy, if you assume, like, and just now I have said, if we have a staircase like this, then if you assume uh, each stair has energy epsilon ij, something like that, then I forget what we have total energy and number of total internal energy and total number of particles. We can define a new variable like small u, which is u over n. This is called the energy per particle. Means we can distribute particles in any number of ways in our energy levels, but we have to define a parameter which will be informative for us. Like, this will tell the number of this will tell the energy per particle of a system. So we will define this parameter like this because it will be constant for our system. We will assume this to be constant for our derivation. So if the number of particles increases, then the total internal energy also increases, so that this parameter remains fixed. Okay, then I have written the form for FQ also. This FQ I have written some multiplication of 1 plus some q. This I can write as e for, because I have to compare with this left hand side, so I need this FQ in this form of exponential. So I assume some function as minus n minus I n, some arbitrary function HQ, which is a which depends on theta and phi, right? So as we have all the exponential form, I can take all the exponentials on the right hand side, integrations, and let them be like that, and I can write e to the power I. This is, I can take common n. If I take common n, then this will be capital U over capital N, and the second term n is there, I can take common. In the first term there is theta, I forgot about that, and in the second term I can take common n, then remains phi, and from the third term I am taking common in. So what will remain? Minus HQ, which is a function of theta, theta and phi. Right. Now let's assume this these many parameters to be some variable w. These things I am doing to simplify uh, my calculation, since I am assuming this to be a different function. So initially the motive is that we have to get rid of this theta and phi, and we have to turn them in such some variables that are measurable, like u, n, t, and these parameters. So the idea is that as we vary theta and phi, this entropy will vary, right? As just imagine there is a space with theta and phi variable, and then this is entropy. So as I vary this theta and phi, my my entropy will change, something like this, something like this, some function, it will change. But at some point of theta and phi, some function like this, let's assume. So at some point we will get some maximum value of entropy. So we need to find that point in that space in theta and phi, then we will rename those variables. So let's name this maximum saddle. Means you are maybe familiar with the saddle point methods. Means if a graph there is a maxima or minima, we have to find the maximum and minima point from that graph. So I'm naming this point to be theta star and phi star. So we need to find this point so that our entropy will be maximum. Because why we are doing this? As in the last class, I have told you, if this microstates, they are varying, and we have limited number of microstates, the entropy function will go up and it will reach an equilibrium. Then after that, if we do means apply some catalyst or apply some external energy, the entropy can decrease. So this is the most stable point for the entropy. So this is a maximum also. So in this space also, you can see we are expecting a maxima for entropy, because this is the equilibrium point. So we need to find this theta and phi variable for the equilibrium. So what we have to do for that, we have to do the derivative of this function with respect to theta and phi. Then we will equate them to 0 and we will find theta and phi variables from them. So those by equating we will get some theta. Just we are assuming that the maxima is at theta star, so we will put theta as theta star and phi as phi star. Phi as phi star. So then we can get these points and we will see what they are telling about our system. So we have defined this parameter as w. Just one second. पापिया, मेरा पार्सल आया है ये। हेलो।
हेलो।
हाँ भैया।
अरे फ्लिपकार्ट से बात कर रहा हूँ।
हाँ हाँ भैया, आ रहा हूँ भैया।
ये किराना ना इधर फूलों की लिस्ट है।
Okay, so we have defined a function w, so we have to do the derivative. We have to do the derivative of this function, and we have to equate it to 0. So if we do the derivative of this some e to the function, then what we will get? We'll get some e function, then we have to apply chain rule and we have to do the derivative of this term. So I'm not wasting more time. I'm simply doing the derivative of this exponential term. So what we have in the exponential, are you guys following, or are you guys lost? I can make it simplified what I'm trying to do. Actually, sir has told you to derive this saddle point. So have you tried, any of you? In the fifth lecture, he has told you to derive this, applying this saddle point method. You have to find phi star and theta star. Have any of you tried? So I assume no. So that's why I'm trying to I'm showing you the derivation for that. That homework you have given, I'm doing that. Okay. So we have to do the derivative of this w function with respect to theta and with respect to phi. This w function we have defined here. This exponential term I am taking as w, and we will do the derivative with this unknown parameters theta and phi, and we are assuming the maximum will be at theta equal to theta star and phi equal to phi star. So we have w, this we have defined as small u. Okay, so this w is I phi theta u minus h2. This is a function of theta and phi, right? We can see from here, apart from this n, this whole term I am taking as I, n and w. W is a function of theta and theta phi, where this rest are w. That's what I have written here. And this hq, as you might be remembering from the class, this hq was I over n log of hq theta phi, or you can check from here. We have defined here hq. You just have to take log of both the sides here. You have to just take logarithm of both the sides. You can find hq as I over n logarithm of this fq function. And sometime before I have written the fq form as 1 plus some exponential q was there, some q power, and depending on that q value it can be fermion or boson. So let me write down this, sorry, this fq again. This fq is product of j equal 1 to infinity 1 plus q e to the power minus I theta epsilon j e to the power minus I phi whole to the power q, right? So depending on this q value, this distribution can be fermion or boson. Q is plus 1 fermion, q is minus 1 boson. So now we have to do the derivative with respect to theta and phi. Let's take derivative of this function with respect to theta, and we will equate this to 0 at the point theta equal to theta 0, because we are assuming at this point this function will be maxima or minima, so we will equate it to 0. So we have w here, we can do the derivative with respect to theta, then phi is independent of that. We can assume at theta equal to theta star, phi will be at phi star, because our saddle point will be at this point theta star and phi star. So as we are considering both the variables, we can assume the other variable to be at its saddle point or its maxima. So first term will be 0 as this is independent of theta. So from the second term we will get I q, then I have to do the derivative of this term. So I have I over n logarithm of then product j equal to 1 to infinity, and I have this term. I am not writing it again, 1 plus this term. So you see logarithm of product, let's say logarithm of some functions you have u1, u2, u3, something like that, then you can write it as log of u1 plus log of u2 plus index. This term you can write as product of some index from I to infinity ui. So you see logarithm of product of some variable you can write as log summation. So I can write this as sum of log of ui, where I goes to 1 to infinity, something like this. So I will use that this, just remember. Okay, so far I have IU, then I have to do the derivative of the logarithm part. So I have 1 I here and h function I have written as this in over this logarithm. So I have 2 i's here, 1 and 2. So this is minus over n, then logarithm of this product, then I can write it as summation of logarithm. This function I can write 1 plus q e to the power something and q. Then I have to do the derivative of this with respect to theta. Right. This is I u n minus 1 over n summation, and I have to do the derivative of logarithm. Then this will be 1 of logarithm of derivative of a logarithm is what, 1 over that variable. So 1 of 1 plus q e for something, or you can take this q value to the front as it is independent of theta. We do not have to worry about that. E to the power something, then this e to the power what do we have in this form, e to the power minus I theta epsilon j and minus I phi we have here. Okay. So we have theta dependence here. So its derivative according to chain rule we will get minus I epsilon j and the same function e to the power minus I theta epsilon j minus I phi. So what we have, derivative of this, and we have to take this as theta star phi star, then we have to equate it to 0. So let me write it clearly. Here we have del of w by del theta as I u minus q of n summation over j equal to 1 to infinity and we have minus I epsilon j e to the power minus I theta star epsilon j minus I phi star, and in the denominator we will have 1 plus q e to the power minus I theta star epsilon j minus I phi star. Then we have to equate it to 0. So what we will get from here? So we can solve this and we will get the number of the energy per particle. We will get this as summation of j 1 to infinity. We have q minus I epsilon j e to the power this form, and in the denominator we will have 1 plus q e to the power this term. So see, there should be n in the denominator, so I will write this one by n. So we found something interesting from here in terms of this theta and phi. So you remember this is u over n and we have n here. We can cancel this, and we will get the total internal energy in terms of these variables theta and phi. Say e to the some term 1 plus q e to the some term. See, so we started from some arbitrary form e to the entropy, and where we take some general form of these variables, where this can describe both fermions and bosons depending on the q value, and we are trying to find a maximum entropy or equilibrium state for this function. That's why we are trying to take the derivative with respect to theta and phi to find the saddle point, and on this process we have to equate it to 0. So during equating it to 0, what we found? We found this u, which is total internal energy, is function of this theta and phi. Similarly, if you do the derivative with respect to phi, we will get at point theta star and phi star, we will get some hello. Do you have any doubt, Swarna? Hello. So when you do this, you will get total number of particles like this form in terms of theta and phi. So I am not doing this. You guys can do this, and this is simple derivative using chain rules. So let me write down the final product. So similarly, you can find this n value. So what we got? U will got summation over j 1 to infinity, and we got this epsilon j, and we have done some mistakes. That's why we got q. It should be q square. Okay, we did something. No, we didn't consider this one. So when you do the derivative, you will get q from here 1, and from the power you will get 1 q. We have, see, we had 1 q here, so this should be q square. Q square is q value, you know, minus 1 or plus 1, so q square will always be 1, so we can neglect that. So this is epsilon j, some e to the power minus of theta and phi function. So in the denominator also we will have 1 plus q, some e to the power theta and phi function, but minus I is there. When you multiply e to the power plus I theta and phi function in the numerator and denominator you will get a form like summation epsilon j over e to the power I theta star epsilon j plus I phi star plus q over this summation, which sir got in his class, but he didn't derive it. He told you to derive these things. So I have shown you the steps. You can do this by yourself, and similarly you can do for n also, where this n will be of the form j goes to 1 to infinity. This will be one over this e to the power I theta epsilon theta star epsilon j plus I phi star plus q. If you check the lecture 4, you will see the forms of u and n in this form. So I have shown you the method so that you can derive these terms, right? So we had w like this form. So if you try another way, if you try to find other variables like temperature and this chemical potential, one second. Okay, so we started from here, e to the power entropy, then we had this exponentials, then we have written this fq in terms of exponential, then we collected all the exponential and named them as n in theta w. So effectively we will have t to the power s is some form of I, n and w, right? So effectively s is I, n, w. So when we try to calculate 1 over t, it will be how much? Del s over del u. So you have s, you can do the derivative with respect to u, then q will 1 over t will be del s over del u. So del s is nothing but this I, n and w, and you have to do the derivative with respect to q now. we had from the initially we had this form where this w, it contains u and this h function. This h function also we have defined here as log of this f theta, and f theta is also this form. So you can do the derivative with respect to u. Now you see this theta, so this w is a variable which depends on theta star and phi star. So we are doing derivative with respect to u of this variable. So we will get terms relating to theta star, del theta star over del u, and del phi star over del u. Then we can, if you do this this derivative, you will get terms like this. If you apply chain rules, and then you will get terms like this. Then we know standard form of one second. Okay, let me clear screen. So we derived form for u. We derived form for u and n in terms of theta and w. Then when you try to find out the temperature by doing this derivative, you will get some forms like this, and with this you will have some coefficients like this, some summation epsilon over 1 epsilon over this exponential plus q and some function like this. Then when you compare this, you can write this as some function of this n u del theta star over del u, then del phi star over del u. Actually, when you calculate this, you will get some terms depending on some like n del phi star del u, something like here I will be there, then something like I theta star, and some term like I u del theta star del u, and we will have some negative of these two terms. So effectively you will get I theta star as 1 over t. So you see these variables theta, this is not any unnecessary variable. This depends on the temperature, which is a measured variable for our system. So similarly you can you can try to find minus mu over t, which is a derivative of del s over del n, then you will get this to be as I phi plus I phi. So this phi variable is now dependent on this chemical potential and temperature. So these variables, they they are not abstract anymore. They are related to our measured variables t and mu, right? So we started from some abstract form of entropy. Actually this is number of microstates. If you take the logarithm of this term, you will get entropy. So total number of microstate, we have some abstract form for bosons and fermions. Then we try to calculate the equilibrium point, that means saddle point. From that we got some relation for the total energy and total number of particles. So from that, we as we have known the formula for temperature, we try to calculate it from the entropy. And what we found? We found that these abstract variables, they are not abstract anymore. They are related to our measured variables of the system, the temperature and the chemical potentials, like that. So they are not abstract anymore, they have form. So we can substitute this theta and phi in that abstract form, and we will get this uh, microstates as some variables of t, mu, u and n, and it will be also dependent on q. So depending on q value, either it will be fermion or boson. So this, up to this part, I was trying to show you that this abstract notation that we have took, they are not abstract anymore. They are physical variables like temperature and chemical potentials. So, and I'm not writing the form. That form you can find from the class, and depending on this q value, either you can distinguish that distribution as Fermi-Dirac. For Fermi-Dirac, you will have some exponential to the power plus for Fermi-Dirac distribution, we will have some 1 plus some exponential term like this, and for Bose-Einstein distribution, we will have 1 over 1 plus some exponential term. So these forms will get from this operation, right? So up to this, any questions? Just I was trying to solve the problem that sir has given as a homework. Like he told you to derive by yourself. I couldn't derive it all because my pens are not working properly. Hello. Do you have any questions?
No.
Okay. Then we'll go to problem section. Then we'll do some problem. So we will do some problem regarding the last week's class, as So I have stored this Sakharov tetrode formula for entropy for classical ideal gas. So what is the question? That what will be the change in entropy per particle of an ideal gas subject to slow expansion of our initial volume from V to 2V, keeping the temperature and number of particles fixed. So let me write down this formula. So this Sakharov-Tetrov formula was like S equal to n logarithm of EV over n AQ plus n plus 3n over 2 log of Q over n. Some constants are there that we do not bother because they are constants. So as the question says, the number of particles is fixed, means this n is fixed, and this temperature is also fixed. So in our system we have constant number of particles and temperature is also fixed. That means the total the energy per particle Q over n, this is also fixed. Means we are assuming this is fixed, that's why as a result of that this will also be fixed. So these are all constants now, these all the terms are constant now. What is the variable here? Only the volume. So we'll try to vary it from V to 2V. So we have this term. So from this term only V is variable. We can take all other terms as some constant K. Then we can write this term as log of n minus, let's assume this K is in the denominator, then this will be log of K. This is some constant and there is some other constant from this term, right? Now we will try to vary this entropy. So we have entropy as a function of volume, so we can take the derivative of entropy as a function of volume. What we will get, these all are some constants, so they won't depend on B. What is the variable now? Sorry. This is B. So this is B. The only variable is here log V. So all other terms are constant, so we do not have to bother about them because their derivative will be 0. So we will get, there is a constant here n, and derivative of log V is 1 over V. So what we got, this change in entropy over change in volume as n over V, or partial derivative of this thing as n over V. Now we can do one thing, as V is variable here, we can take this delta V to the right hand side, so we will get delta S is over b. Then so for finding s, we can take integration on both the sides. So this will be n over b del b, and here in the question we are given that volume is varying from v to 2v. So we can do this integration. What we will get, n, the integration of 1 over b will be logarithm of b, and the limits are from b to 2b. Let me clear the upper part. So what we have, s as n ln b going to b to 2. So what will be this one, n ln of 2b minus ln of b, or this is n ln of 2b by b. This is equal to n ln of 2. So we have s as n ln 2. So what is the question? The question is now what is the change in entropy per particle. So entropy per particle means entropy over n. This term will define as entropy per particle. So this is ln of 2. So the right answer is ln of 2. Right, you understood, right? Well, I have defined this formula first, then we check that all other terms are constant for this question, like the number of particles and u, they all are constant, or the only variable is b. So if we take the derivative of entropy with respect to b, we'll get a form of b. Then we can take the integration of both the sides, which will give us the logarithm form, and we can take the limits as b to 2b. Our volume is varying from b to 2b. So from that we got s is n ln 2. So we what is the question? Entropy per particle. So we can divide this n from the left from the both sides. So we will get entropy per particle as ln of 2. Right. So coming to the next question. So the question is, we have given a distribution, as you can see from here, that we were trying to solve previously in this class. So we have this form of this number of microstates. This e to the power s means the number of microstates, and we have this form as this one. And if q is positive, this defines fermions. That means we can put only one particle in a system, and if q is -1, we can put any number of particles in one energy level. So you can assume them as energy levels or stairs, whatever you want. So if q value is 1, we have fermions. Fermion means we can put only one particle in one energy level. And if q value is -1, we will get a distribution which is called Bose-Einstein distribution. By solving this, then we will get a distribution for boson, where we can put any number of particles in any energy state. So here j is the step. So let me draw this. can draw some stairs where this j value represents the stair number, like j equal to 1 represents first stair, j equal to 2 second stair, j equal to 3 third stair, and like that. So in total we have m number of stairs. As you can see, we have m number of stairs. So the question says, if q value is 1, no more than one particle can occupy each stair. So for q value equal to 1, we can put only one particle in each stair, and for q equal to -1, there is no restriction, we can put any number of particles. So in this question, this epsilon j value that I have talked about, what is this epsilon j? This is epsilon j is the energy of this jth number of stair. So each stair will have some different energy. So if a particle is there in this jth state, I put a particle here in this stair, then what will be its energy? Epsilon j. If two particles are there in this stair, then the total energy will be 2 epsilon j. If two particles are there and one particle is here, so the total energy will be 2 epsilon j plus epsilon j plus 1. That means we total energy we can write as number of particles in jth state and energy of that jth state, and it will go from 1 to whatever number of stairs are there. So in our question, it is clearly saying that Ej means the jth stair has energy Ej, and note that this formula works only for u and m and epsilon j, all are integers, and for our case this Ej is j. Okay, what that means, the stairs, if its energy is Ej, then simply for our question it's j. That means if we are starting from stair 1, then its energy will be 1. For stair 2 we have energy 2, for stair 3 we have energy 3, and so on, right? And we are given q equal to 1, that means fermions. Q equal to 1 means fermion, that means we can put only one particle in each stair, right? And m equal to 4, that means we have 4 stairs, that means we have 4 energy levels, right? M runs from j equal to 1 to m, that means it represents the energy level. So m value 4, that means it represents there are 4 number of energy levels or 4 number of stairs, whatever you like to call it, right? And then we are told to calculate SUN2, that means we have n equal to 2, that means we have 2 particles and 4 stairs, and they are fermions, that means we can arrange them like one in each stair, and we have total number of 4 stairs. So we have to arrange them in such a way, and we have to find the entropy for that, right? Let's do this. Okay, so according to question, we are given number of particles as 2 and number of energy levels are 4, and q value equal to 1, that means fermions So we have total 4 energy levels: 1, 2, 3, 4, and each energy level we saw that epsilon j equal to j, means if first j represents 1 here, this energy is 1, then this is 2, this is 3, this is 4, and we are given 2 particles or 2 balls, whatever you like to call them, and we have to arrange these 2 balls in these 4 energy levels. And what is the condition? Only one ball can go to one energy level. We can't put 2 balls on single energy level, so we have to arrange them like that, and we'll find the entropy for that microstate. So what we can do, we can arrange these 2 balls as 1 1 0 0. Let me this 1 1 0 0 or 1 0 1 0 or 1 0 0 1. Similarly, I can do 0 1 0 1 0 1 1 0 and 0 0 1 1. These are the only ways, right? Or you see any other part that I am missing? Anyone? As they are fermions, we can arrange them single, so we can't put 2 particles in single state. So these are the only ways we can do their we can arrange these particles, right? So these are the only ways we can arrange. So how many particles are how many arrangements are there? 1 2 3 4 5 6. So we have 6 arrangements for this, and am I missing something? There are 6 arrangements, right? One second. पापे मेरा फ़ोन दो ना. फ़ोन क्यों किया था फिर? So we can calculate their internal energy also. So there are 2 particles in first and second, so internal energy will be 3. So for the second case, here and here it will be 4. First and 4, then it will be 5. Second and fourth, 2 plus 4, it will be 6. 2 3 is 5, 3 4 is 7, right? So what am I doing? I am considering their indistinguishable particle, but in question it is not given they are indistinguishable, so we can arrange between them. So what I can do, I can arrange between these two. I can put one ball here, let's call it A, then second ball here, let's call it B, or we can arrange like this, B here and A here, right? So for this, how many configuration I'll get? I'll get 2 for this 2. Here also I can get 2, 2, 2, here also 2. So how many microstates I have? 3, 6, 12. So number of microstates are 12 for this state. So what will be the entropy? Entropy is Kb ln of number of microstates, which is 12. Did I miss something? Q equal to 1 means fermion, right? Can anyone correct me? Q equal to 1 equal to fermion or boson?
Q is 1 is fermion.
Okay, so we have done it right. So entropy, how much we got? Yes, we can take Kb equal to 1, so entropy is ln of 12. If we are considering distinguishable particle, if we consider indistinguishable particle, then we cannot arrange between them two. Then our microstates will be only 6. We do not have to arrange between them. So for indistinguishable particle, we have entropy to be ln of 6, right? We can do like let's assume these are not fermions anymore. We are given Q equal to -1, so we can distribute these two balls in any arrangements now. So what will be the entropy for that? Fixed space. Okay, here I have white space. So I have 4 states, and now they are bosons. And let's consider there are
Can you show me the before slide that you have calculated for in Kb in 12 for fermions?
yes, here, here.
Yeah. So when we go for bosons, it comes around S is equal to in of 6.
No, no, no.
Ah,
It's about distinguishable or indistinguishable.
indistinguishable.
So if they are distinguishable, I can arrange between them. Means there are two particles in 1 and 2. If I can distinguish, I can call this ball as A and this is B. Then I can do one more thing. I can put B here and
Yes.
A here.
Ah.
So there will be two configurations. So this this is for distinguishable, and this part is for indistinguishable. And 6 is for indistinguishable because I don't have to arrange between A and B. they will look the same. So
Yes,
I'll get
yes, 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 yes. That is the thing I have confused with both the things.
So we checked for fermion case. Now let's check for boson case. So we have freedom now. Like we can arrange, like we can put any number of particles in any state. So let me label this in energy labels. So we have two particles. We can arrange them between these four states. So I can do like I can arrange them like the fermion case. I got six configuration from there. See here, if I want to arrange one state like fermions, like I want to put one ball on one state only, then we will get six states, six kind of configuration. Let's assume for indistinguishable first, then we'll talk about distinguishable. So for indistinguishable case, arranging between these one and two states, they will look alike. Means A and B are same, so there is no need. So if I try to arrange them in in single particle in each state, so we will have six energy states. Then now put two particles in each state. So how much we will get? We will have configurations like 2 0 0 0 2 0 0 2 0 0 0 0 2 0 0 0 0 2. I am putting two particles at a time in each state. For the first state, the energy will be 2. For the second case, it will be 4. For the third case, it's 6. And for this last case, it's 8. So I have four extra configuration for bosons along with this 6 configurations that I took from fermions. Means these boson particles I can arrange them like fermions also. Along with that, I can put two particles in single system. So I'll have additional 4 ways of arranging these two particles. So if they are indistinguishable, I do not have to arrange between the balls. If they are indistinguishable also, if they are in same states and B, there is no meaning of interchanging A and B as they are in same states. So if they are distinguishable, there is no other way. We have this configuration. Means there are two balls in first state. Means if they are distinguishable also, there is only this kind of state. But like particle in two different states, if they are distinguishable like A and B, I have a scope, like I can arrange these two in a different way. Like I can put B here, then A here, then I can arrange this system as two different way. But for this case, I do not have that luxury. I do not have other configurations. So there are four ways, four additional ways I can arrange them for boson case along with this 6. So total 10 ways I can arrange them if they are distinguishable. But if they are indistinguishable, as I saw here, like I can arrange the bosons like fermions also, then each state will have two different ways of arranging. So we will have 12 from here and 4 from here. So in total 16 for distinguishable case. For indistinguishable case we have 10. So for indistinguishable case we have entropy as ln of 10, and for distinguishable case we have entropy as ln of 16. Right. So this is a form what Boltzmann gave. This is Boltzmann formula, like entropy is Kb times logarithm of total number of microstates. We have used that and to calculate the entropy, but there are other formula also which we call like maybe for not for this question. Okay, it would be better if I could write them all in a single sheet. Let me write all others. 1 1 0 0 1 0 1 0 0 1, then 0 1 1 0 0 1 0 1 0 0 1 1 6, right? So its energy will be 3, this energy will be 4, this energy will be 5, this is 5, this is 2 and 3, okay, this is 5, this is 6, this is 7. So I have configurations like this, and I have total internal energy distributed like this. So I can see there are 2 5, 2 6, 2 4. What that means, this configuration and this configuration, they have same energy. So what this configuration will call, they will call degenerate configurations. They will call degenerate configuration. That means they will have same energy but different configuration. Means I can put 2 particles in second state, or I can put 1 particle in first state and third state. I'll have same energy. Similarly, for 5 total internal energy 5, I have 2 configuration, means these 2 states are degenerate. Similarly, for this state and this state, their also energy have same, so these 2 are also degenerate. So I have, let's assume only indistinguishable case here, then I'll go for in distinguishable case. So I have how many 6s? 2 6. How many 5s? I have 2 5s. 4s, I have 2. Then 3, I have 1. 2, I have 1. Then 7, I have 1. 8, I have 1. How many? 6, 7, 8, 9, 10. Here also 6, 4, 10. Yes, right. So there is another entropy formula in terms of probability. Like if someone asks you what is the probability of the 2 particles of getting energy 5 or 4, like if someone asks what is the probability that this 2 particle is arranged in this 4 configuration, that you will get energy 5. So I have 2 ways I can arrange them. So what is the probability of this 5 energy, that is P equal to 5. What is the probability? I have how many configurations so far? How many energy levels I have? 3 4 5 7. So I have total 7 configurations of energy. And how many, no sorry, I have total 10 configurations. I have total 10 configurations. Out of them 2 are giving me total internal energy 5. So what is the probability of getting total internal energy? It's 1 over 5. So the probability formula in terms of probability, the entropy formula in terms of probability is like this: summation over I pi ln of pi. So where this pi is the probability of that state, means being in that state. So for u equal to 5, I have probability 1 over 5. So P5 is 1 over 5. Similarly, I can write P6 is also 1 over 5, and P4 also I can write as 1 over 5. What will be P3, 2 and 1? They are only one state, so P, I am denoting this subscript as energy. So P8 is 1 over 10. So I have one configuration out of 10 which has a total internal energy of 8. So what will be the entropy for this kind of arrangement? Let me show you. So the entropy is summation over pi ln of pi. So what will be the entropy? Let me start from this 2. So for 2 I have probability 1 over 10 ln of 1 over 10 means 0.1. I can write this 1 over 10 as 0.1, plus for 3 also 0.1 ln 3 ln of 0.1. Similarly for 7 and 8 also I have to write 2 more terms, but for this 6, 5 and 4 I have to write as it's 1 over 5, so means 0.2 ln of 0.2. How many are there? 3 such systems are there. So for this system there are 4, 1, 2 and 2 will be there. So effectively I can write 0.1 ln of 0.1 into 4 plus 0.2 ln of 0.2 into 3, right? So do anyone have calculator? Can someone calculate this and tell me the number? Let me calculate. And 0.1
Coming around minus 1.88.
minus 1.88. Okay.
Yeah.
Okay. So maybe I have okay. I told you this formula is wrongly. So S is minus summation over pi ln pi. So effectively it will be 1.88, right? So this is one method. This is the correct formula. So from this method you got 1.88. Now you apply the other Boltzmann formula. From that you calculate the entropy. How much you are getting? it will be the ln of total number of microstates. How many microstates I have? This is 6 and 4, 10. What is this value? 2.3. So I am getting 2.3 here and 1.88 from this formula. As the number goes high, we'll get numbers very close to each other, but they are very different formulas. They are describing entropy. According to Boltzmann, the entropy is like this, and from what is this called, probability form, by enumerating you can get entropy like in this probability form. They are very close to each other. We computed them, and both of them are non-zero, right? Which of them has highest entropy? We have checked. Do you have 6 energy level? What is this? Here, okay. So we have 6. What is the question here? So we are asked, like, U equal to 4 and number of particles equal to 2. What is the entropy? We can use this ln of omega formula, or this enumeration form, summation over pi ln of I pi for this particular value of configuration. So we have calculated all these configurations here. So how many 4s we have? 2 4s. So total energy equal to 4, and for 2 particles we have 2 microstates, so entropy is 2. And what is the probability of that getting 5? It's 2 over 10, so it's 0.2. So what is this entropy according to this? 0.2 ln of 0.2. We can check what are these numbers. These are what we calculated it. These are for bosons, and they are distinguishable. Just remember that. If you consider them to be indistinguishable, then we will have extra arrangements, like all these 6, they will have 2 different configurations. So we will have two states with energy 3, 2 states with energy 2, and 2 states with 7 and 8 energy states. Maybe not 8 we can't arrange, so it's only these will have 2. So 4 we have 2 here. Actually you can do it with your pen and paper. You check how many 4s are there, if they are distinguishable now. So you will have 2 different configurations for each of the states. So then you will have 2 4s here, 1 4 here, so total 3 degeneracy and total number of states will also be different because you have 6 here, and so 6 into 2 12 and plus 4 16 configuration, and out of those 16 configuration 3 states are giving you energy 4. So what is the probability for that? P of 3 is 4 over 16. Then probability will also change, then entropy will also be changed if you consider only distinguishable case. You can check that with a pen and paper. Use your homework. Okay. We checked this question is for the previous one. You can do it generally. You can calculate for both the cases, boson distinguishable, 2 you calculate for fermions distinguishable, then 3 you calculate for bosons indistinguishable, then 4 you calculate for fermions indistinguishable. You will get different entropies uh, for these cases. Let's assume one case and we will calculate the entropy for each of these terms, and we will check which is the highest entropy. So for this I'm just considering boson and indistinguishable. So this case we have calculated this sometime before, so I am checking this. So according to this my entropy is ln of 2. So similarly for this case, u equal to 5, n equal to 2, what is the entropy? Let's stick to one form of entropy only. Let's take Boltzmann entropy. So how many 5s I have in the last case? 2.
5s.
2 5s. So there are 2 microstates with 2 microstates which are giving total internal energy to be 5. So my entropy, this will be ln 2. Similarly, how many 6s I have? 2. So for that also 2. For 3 case, how many 3s I have? 1. So for this entropy is 0. So for this entropy is ln 2, this is ln 2, this is ln 2, this is ln 1, that means it's 0. So these 3 are giving me same entropy for this boson and indistinguishable case. You can check for distinguishable case, you will get different numbers here. So you can compare which entropy is higher than the other one. You can check for the this 4 configuration. I just told you how to do this. We just did for fermions. We have to do what? We have to arrange only one particle in each state. We cannot put 2 particles in same states. And in this arrangement also, if you consider distinguishable, then I can distinguish this particle from this particle, then I will have additional distribution among them too. So I will have additional microstates for each state. This is for fermion. For boson, I can put any number of particles in each state. So and there is no meaning of arranging these particles in these configurations. If bosons are here, if they are bosons also, if one is here, one is here, A and B, I can distinguish between them, and I can rearrange them, like I can put B here, then A here, then I can have additional ways of arranging. But if I put in two particle, but they are distinguishable, there is no meaning of rearranging them. They are same, right? So similarly, you can calculate the microstate for these four configurations, and you can check the entropies for each case. For some boson distinguishable case, maybe you are getting this one is high. For fermions, you will get something like this one is high. I'm just saying, you can just check this. You can note down this question and you can check for each configuration. This is a good exercise for you. So coming to this next question, what we are given this microstate formula. This is e to the power s, which we have this form similar to the last question. With plus 1 it's fermion, minus 1 it's boson, and these are integers. And for this question we are given like q is minus 1, that means they are bosons. Here you see q equal to minus 1, that means they are bosons. So they will follow Bose-Einstein statistics, Bose-Einstein distribution. And m equal to 4, that means I have 4 energy levels, and each energy level is J. That means first is 1, second 2, 3 and 4, right? So what is the question? Find u of 6 and 2. That means I have to arrange my balls so that, or particles, so that my total internal energy will be 6, and I am given 2 particles. So we did this in last question also. So you have to arrange these 2 particles. First you have to, I am saying you the method, you can arrange one particle in each state. You will get 6 configurations, and you can put 2 particles in single state also, then you will get 4 configurations. If they are indistinguishable, this is it. But if they are indistinguishable, you can arrange between these 2, then you will get 2 configuration for this, 2 for this, and something similar like this. But you won't have anything like that for this configurations. There are 4 configurations like this. So you have to calculate total internal energy for each configuration, like 1 here and 1 here. What will be the total energy for this? 2 plus 1, 3. So similarly, if you have 1 0 1 0, one particle here, one particle here, we will have 3 plus 1, 4. Similarly like this. And from each of them you have to find 6's. How many 6's are there? From this also you have to find total number of 6. How many times this 6 is repeating? So you have to find the microstate corresponding to this internal energy 6. What is this? You can calculate this, then we will get entropy as ln of this value. So you can do this. Similarly, you can calculate the how many forces are there in this set, as is mentioned here, an indistinguishable particle. So you won't have this configuration. So indistinguishable, these are 6, these are 4. So you have to find how many for this. Calculating this, how many 4's are there. So this is for 6. How many 4's are there? You have to calculate. Then you will get entropy for that also, and for this case also. You have to find how many 7's are there. That we know, we have calculated here. No need to calculate again. We have 1 7, right? So for this 7 case, S of Q equal to 7 and number of particles 2. What is the entropy? We have only one microstate corresponding to this energy 7. So this is Kb ln of 1. Ln of 1 is 0. So this is 0. Similarly, we can do what are the others. We are asked 4 and 6. Let's check. As it is already done, we can do this here. How many 4s we have? 2. So S of U equal to 4 and then particle 2, this is ln of 2, and for 6 equal to 6. Remember, we are given only indistinguishable particles, so these won't be counted, because that means we do not have to arrange between them. So we already did for these things. So 2 6s we have here 1 and here 1, so we have 2 6s. Here this is also ln2. So what will be the answer? So 6 means ln2, 4 means ln2, and for the last one we are getting entropy 0. So this is the right answer. And you can do this by enumerating also. Enumerating means by that another formula I have given you for entropy. That means summation over Pi ln of Pi. So let's assume for entropy for U equal to 6, N equal to 2. So how many states we have for 6? 2. And how many total microstates are there? There are total 10 microstates. Let's calculate. See, we have 2, 2, 2, sorry, there are more than 10, I think 6, 7, 8, 9, okay, sorry, there are 10 microstates, 2, 2, 2, 1, 1, 1, 1. So total 10 microstates. Out of them, 2 are with energy 6. Where is the page? So 2 out of 10 are corresponding to energy 6. So probability of getting U equal to 6 is 2 over 10. That means 0.2. So for this configuration, what will be the entropy according to this formula? So this will be 0.2 ln of 0.2. You can calculate using your calculator what it will be. This number, sorry, this is minus 0.2 ln 0.2. Similarly, for S equal to 4, N equal to 2, we have 2 configurations out of 10 which are giving us total internal energy 4. So probability of U equal to 4 is equal to 2 by 10. So this is also 0.2. For this also entropy will be this much. For the last case, S equal to U equal to 7, N equal to 2. For this case, we have 1 out of 10. So we have probability of U equal to 7 as 0.1. So for this case, S equal to 1 for N equal to 2 is minus 0.1 ln 0.1. For this also, I think you will get 0. You just cross check in this method and Boltzmann method. You will have some different numbers, but the behavior will all will be similar. In this question, it is asked you to 1 second. Up here. So we saw two different methods of calculation of this entropy, right? In this question also, they are asking you to explore these two methods and find the entropy. Like, we got this answer, right?
I think you have muted.
Oh, sorry. So I was saying there are two different ways of calculating this entropy. You explore both of them and calculate the entropy. And in this question, they are telling you to explore these two ways also. Enumerating means you have to calculate the entropy using this probability method, and you know already the Boltzmann method, and we got this answer also using Boltzmann method. Right. So coming to next question, we have similar distribution. This time we have 5 particles and q equal to 1, that means fermions. And what is the m value? 4. We have 4 levels, but we have 5 particles. How will you arrange them? We can't. If they are fermions, we will have only one more will be left. So there is zero way of arranging this. So if you evaluate this one, then we will get 0, because you will always have one extra particle left. So but if they are boson, you can put that extra particle in any of the states, right? So for this, answer is 0. Any doubt so far? Okay, you learn two ways of calculating entropy, and you have time to explore them, both of them. One is by probability, and one you know by Boltzmann formula. You explore both of them. Yeah, hello.
No, actually, I have doubt in an assignment one. That
Hmm.
is, there are 5 identical marbles in 5 staircase problem. That is question number 3 of week on assignment. Can you discuss that question?
Yeah, yeah, sure. You tell me the problem.
Actually, there are 5 identical marbles, and the steps staircase steps is 5 steps.
Okay.
What is the entropy? What is the maximum entropy for the total energy?
And what is the energy?
Entropy. Yeah, yeah. Actually, there are. I'm getting 14, 15, 21, etc.
Hmm.
The answer is U equal to 15, the maximum. Can you discuss something in that question?
Okay, let me check the question first. Question number.
Question number third question.
from this slide or
Not in this slide. That is in the assignment question.
oh, assignment question? Then I don't have.
Yeah,
Okay, then you tell me the question. There are five.
there are five identical marbles
Hmm.
on five staircase step,
Okay,
and it has a staircase of five steps.
and what is the energy of each
Uh,
step?
Energy of each step is 1, 2, 3, 4, 5.
Okay,
There is a restriction that no more than two marbles cannot be seated in a particular step.
okay,
So, what will be the maximum entropy for the total energy is the question.
okay. What will be the maximum energy?
Maximum entropy. What is find the entropy is maximum and the total energy is the options given are U equal to 0, U equal to 14, and energy is 50 and energy is 22.
Okay, so then we have
And that there is a number of possible arrangement of atoms, since it is two atoms can be seated in step, right?
yeah. You start with one, like you have five,
Yeah, that I have calculated.
one, one, one. And they are
Five ones.
indistinguishable or indistinguishable?
Uh, identical,
Identical. That means
identical marble. Mm.
indistinguishable. Okay,
Yes,
so
yes,
we have one this kind of arrangement. Then only twos are there. I can put two in first, then others are
yeah.
one, so five. So similarly, you can rearrange this configuration accordingly. How many you will get? Two, one, and you can do two, two, one. This configuration you can explore. How many are there?
So one,
This configuration is always one you have, but
one,
let's
yeah.
explore this configuration two, one, 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 zero. How many ways I can arrange this configuration?
One, two, three, four, five, six,
Two, one, zero,
seven, eight.
two, one, one, zero, one, two, zero, two, one, zero, one, one,
Yes, two, one.
two, zero, one, 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 or two, zero, two, one, one, one. Now I can play with two. I can put this as two, one, 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 two, one, zero, one, one, zero, two. These are the all possible ways I can arrange this two, one, one, one. Similarly, you have this configuration two, two, one, two, two, one, zero, zero. You have to arrange them. How many you are getting? Are there any possibilities? You other possibilities other than this? You see. Let's
There are other possibilities also. The first step can be zero, and the second step may be two, zero, one, one, one.
yes, that's here 20111.
Uh, yes.
Okay,
Okay,
so everything related to this numbers I have already done. So you have to do this this one,
okay,
this three non-zero numbers
okay,
and two
okay,
zero. Then you have to calculate the total internal energy for each of them, and
okay.
you have to calculate how many are there in 15 corresponding to 15, means how many microstates are corresponding to 15. Then you will find this micro entropy for this, and similarly other internal energy also you can find. You have to arrange this. There is only one, and
So totally one state in five marbles, and there are eight states, and there are three states. Okay, then I can calculate it.
yeah, you have to arrange this. I didn't do this. You have to arrange this.
Okay,
This.
okay.
Yeah. Okay, then we'll meet in next class.
Yes.